Right now, while you're watching this, something is happening 200 kilometers above your head that almost nobody on Earth is thinking about. There is a shell around this planet. It is invisible, it is moving, and it is filling up. It is not a cloud, it is not an asteroid field. It is not a natural feature of the solar system at all. It did not exist before 1957. It was built before you were born, before the internet, before anyone alive had a phone in their pocket. And it was built entirely by us, one launch at a time, without anyone ever deciding to build it. There are an estimated 1.2 million fragments up there, larger than 1 centimeter. 1 centimeter. Smaller than a grape. And every one of them is moving at roughly 28,000 kilometers per hour. At that speed, a chip of aluminum the size of a grape hits with the energy of a small car on the highway. It does not dent a satellite, it ends one. And here is what makes this different from every other space story you have seen. This is not a threat to a spacecraft. It is a threat to the door, to the ability to leave at all. The researchers who study this are not using words like interesting or concerning. They are using phrases like cascade, runaway, and irreversible on human timescales. This is the story of Kessler syndrome. And here is the part the headlines are not telling you. It is not just what the models predict. It is what already happened, twice, in orbits people still use every single day. It is what is happening right now in 2026, as more satellites launch in a single year than were launched in the first 40 years of the space age combined. And it is what happens to the fragments that are too small to track and too fast to survive, the ones nobody can see coming. Stay with me, because by the time this is over, you will never look at a clear night sky the same way again. In 1978, a NASA scientist named Donald Kessler was doing a job almost nobody wanted. He worked at the Johnson Space Center in Houston. His background was in the study of meteoroids, the natural dust and rock that drifts through the inner solar system. His task was mundane. Count the particles, model the risk, tell the engineers how likely it was that a spacecraft would be struck by a grain of natural debris. It was bookkeeping, statistics about dust. But Kessler kept noticing something in his own numbers. The natural population was not the interesting one anymore. The artificial one was. By the late 1970s, roughly 2 decades of launches had left behind spent rocket stages, dead satellites, discarded hardware, and fragments from explosions of leftover fuel. Nobody was tracking it as a system. Everybody treated each object as an individual problem. One dead satellite here, one spent upper stage there. Kessler treated it as a population. And populations behave differently than individuals. In 1978, Kessler and his colleague Burton Corpillay published a paper in the Journal of Geophysical Research with a title that sounds almost bureaucratic. Collision Frequency of Artificial Satellites, the Creation of a Debris Belt. The argument inside it was not bureaucratic at all. They pointed out that as the number of objects in low Earth orbit grows, the number of possible collisions between them does not grow at the same pace. It grows faster. 2 objects give you 1 possible pair. 10 objects give you 45. 1,000 objects give you roughly 500,000. The collisions themselves are the problem. Because a collision does not remove objects from orbit. It multiplies them. One satellite becomes thousands of fragments. Each of those fragments is now its own collision hazard, on its own orbit, crossing everyone else's. Kessler's conclusion was that past a certain density, the debris population becomes self-sustaining. Collisions generate fragments faster than the atmosphere can drag them down. The belt keeps growing, even if every nation on Earth stops launching tomorrow. That is the scenario that now carries his name. The turning point was not the paper. Papers get filed. The turning point came 30 years later, when the theory stopped being theoretical. In January 2007, China conducted an anti-satellite weapons test. The target was one of its own aging weather satellites, Fengyun 1C, in a polar orbit at roughly 865 kilometers. The interceptor hit it head-on. That single event created more than 3,000 trackable fragments, and by most counts, it remains the single worst debris-generating event in the history of spaceflight. Not a war, not an accident, a test. Kessler's population of objects had just been handed thousands of new members, in one of the most crowded and most durable altitude bands there is. The bookkeeping was over, and there is a detail in that story worth sitting with. Fengyun 1C was a working weather satellite for most of its life. It watched cloud systems, It helped forecast storms over one of the most densely populated regions on Earth. Its final contribution to the space environment was thousands of fragments in an orbit that will outlast everyone reading this. Kessler himself spent the rest of his career explaining the same arithmetic to progressively larger audiences. He retired from NASA in 1996, before the events that proved him right. He has said, in interviews since, that the part people misunderstand is the speed of it. They expect a catastrophe. What the model actually describes is something slower and much harder to argue with. To understand why this cascades, you have to understand why orbit is fast. An object in low Earth orbit is not floating. It is falling forward so quickly that the ground curves away beneath it at the same rate. To do that at a few hundred kilometers up, it has to travel at roughly 7.8 kilometers every second. That is about 28,000 kilometers per hour. Every object up there is moving at close to that speed, including the junk. Now the chain. Two objects in low orbit rarely travel the same direction. Some go east, some go over the poles. When their paths cross, they do not merely add speeds, they close on each other at a combined velocity that can approach 15 kilometers per second in the worst geometries. 10 kilometers per second is a reasonable working number. At those speeds, materials stop behaving like materials. A bolt does not punch a hole in an aluminum panel. It arrives with so much energy that both the bolt and the panel vaporize at the point of contact. Engineers call this the hypervelocity regime. The impact behaves less like a bullet and more like a small explosion. That is why a 1 centimeter fragment is the number that matters. Below 1 centimeter, shielding can usually handle it. Above 10 centimeters, radar can usually see it coming, and the spacecraft can move. Between those two numbers is the gap. Too big to survive, too small to track. There are an estimated 1.2 million objects sitting inside and around that gap. Here is what happens when one of them connects. The impact releases enough energy to fragment the target. Those fragments do not simply vanish. They do not fall. They inherit the orbit of whatever they came from, plus a small kick in a random direction, which means they spread into a shell of slightly different orbits, all crossing the original altitude band, all still moving at roughly 28,000 kilometers per hour. One object becomes thousands. Each of those thousands is now a projectile, with the destructive capacity of the original, just distributed. Then the clock matters. Below about 400 kilometers, the thin upper atmosphere drags on debris and pulls it down within a few years. That is why the International Space Station's altitude self-cleans, slowly. Above 800 kilometers, that drag becomes nearly negligible. Debris up there can stay in orbit for centuries. Above 1,000 kilometers, on human timescales, it effectively does not come down at all. So the fragments accumulate, and the more fragments accumulate, the more likely the next collision becomes. And the next collision makes more fragments. That is the cascade, not an explosion, a ratchet. It only turns one way, and there is a second source that has nothing to do with collisions at all. Spent rocket upper stages are frequently abandoned in orbit, with residual propellant still inside them. Fuel and oxidizer separated by a seal that was never designed to last for decades. Batteries left connected and cycling through extreme heat and extreme cold, 16 times a day, for years. Those things fail. When they fail, the stage detonates. These are called non-collisional fragmentations, and they have historically been responsible for a substantial share of all cataloged debris. No impact required, no warning. A 20-year-old fuel tank simply lets go, and a single object becomes hundreds. The fix for that one is genuinely simple and genuinely effective. It is called passivation, venting leftover propellant and discharging batteries once a stage has finished its job. It has been standard practice for responsible operators for years now. It does nothing for the stages abandoned before anyone thought to require it, which are still up there, still pressurized, still waiting. Now here is why this is so much harder to fix than it sounds. Ground-based radar and optical networks can reliably track objects down to roughly 10 centimeters in low Earth orbit. ESA's Space Environment Reporting puts the number of objects currently tracked and cataloged at around 40,000. That sounds like a lot. It is not the problem. The problem is the 1.2 million fragments above 1 centimeter that models say are up there, and the roughly 130 million above 1 millimeter. Those numbers do not come from a catalog. They come from statistical models, calibrated against returned hardware, spacecraft surfaces brought home and examined for pits, which means the most dangerous population in orbit is a population we infer rather than observe. You cannot dodge what you cannot see. A spacecraft can maneuver away from a tracked object. It cannot maneuver away from a fragment that no radar on Earth has ever detected. Second constraint: you cannot repair anything. There is no service call in low Earth orbit. A punctured pressure vessel or a severed solar array on an uncrewed satellite is permanent. The satellite becomes debris. It joins the population it was hit by. Third constraint: you cannot remove it easily. Every gram of debris is moving at 28,000 kilometers per hour. To retrieve a single object, a chase spacecraft must match that speed, match that orbital plane, and then capture a tumbling, uncooperative piece of metal with no grapple fixture and no attitude control. One object, one mission. Enormous cost. There are on the order of a few thousand large derelict objects, dead satellites and spent rocket bodies, that debris researchers consider the highest priority removal targets, because each one is a magazine of thousands of future fragments waiting to be triggered. Fourth constraint: nobody owns the sky. Orbital altitudes are not sovereign territory. The debris created by one nation's test threatens every other nation's hardware, indefinitely, and there is no enforcement mechanism that can compel cleanup. And the fifth constraint is the one that makes researchers most uncomfortable. Even if every launch stopped today, the models still show the fragment population in some altitude bands continuing to grow, because the collisions between objects already up there are enough to sustain it. You cannot unlaunch 1957. There is one more constraint, and it is the least dramatic and the most limiting: uncertainty in the tracking itself. When operators receive a conjunction warning, a notice that two objects will pass close to each other, that warning does not come with a certainty. It comes with a probability, derived from orbits that are themselves estimates. Atmospheric drag varies with solar activity. Tumbling objects present changing surface areas. Days out, the position error on a tracked fragment can be measured in kilometers. So operators are handed a choice with no good answer. Maneuver on a low probability warning and burn propellant you will need later, shortening the satellite's working life. Or ignore it and be right almost every time. Thousands of those warnings are issued every week. Almost all of them are false alarms. That is not reassuring. That is exactly how a system trains its operators to stop reacting. Start with the event that turned the model into history. On February 10, 2009, at an altitude of roughly 789 kilometers over Siberia, an active American communications satellite named Iridium 33 collided with Cosmos 2251, a Russian military communications satellite that had been dead since the mid-1990s. Neither one was maneuvering. Cosmos 2251 could not. It had been a derelict for over a decade, an intact, uncontrolled, one-ton object drifting through one of the busiest altitude bands there is. The closing speed was on the order of 11 kilometers per second. Both satellites were destroyed instantly and completely. The collision produced more than 2,000 trackable fragments, plus an unknown but far larger population of pieces below the tracking threshold. This was the first accidental hypervelocity collision between two intact satellites in history. Here is why it contradicted comfortable assumptions. Space is often described as empty, and at human scale that is true. The volume of the shell around Earth between 700 and 900 kilometers is enormous. Picking two specific objects out of that volume and having them meet should be vanishingly unlikely. But orbits are not random, they concentrate. Sun-synchronous and near-polar orbits are useful for imaging and communications, so everyone uses them, which means traffic funnels into the same narrow altitude bands and the same crossing geometries, over and over, 16 times a day. The scale comparison that helps. It is less like two cars meeting in an empty desert, and more like two cars meeting on the only road through it. What remains unresolved is how many sub-centimeter fragments that single event produced. Estimates run from tens of thousands upward. Nobody can count them. They are still up there, at roughly 28,000 kilometers per hour, in an orbit that does not decay meaningfully within a human lifetime. Then it happened again, deliberately. On November 15, 2021, Russia conducted a direct descent anti-satellite test against Cosmos 1408, a defunct Soviet-era signals intelligence satellite that had been dead since 1982. The intercept occurred at roughly 480 kilometers. It generated more than 1,500 trackable fragments, and, by most assessments, many thousands more too small to catalog. The crew aboard the International Space Station were instructed to shelter in their return vehicles as the debris cloud passed. 7 people, sheltering from the consequences of a weapons test aimed at a satellite that had been dead for 39 years. This is where the numbers stop being abstract. The International Space Station has performed more than 30 debris and satellite avoidance maneuvers since 1999. Each one costs propellant. Each one requires days of advanced tracking. Each one only works against objects large enough to be catalogued. For everything below that threshold, the station relies on shielding, layered barriers, designed to shatter and disperse an incoming particle before it can breach the pressure hull. That shielding is rated for small impacts. It is not rated for the gap. It is not rated for 1 centimeter. The comparison that lands. The crew is protected the way a helmet protects you. It works against the debris you are not going to see anyway. It does not work against the thing traveling at 28,000 kilometers per hour. What contradicted the model here was not the physics. It was the behavior. Kessler's 1978 paper assumed the debris population would grow through accidents and accumulation. It did not model nations deliberately choosing to fragment their own hardware in the most durable orbits available. 4 such tests have now been conducted by 4 different nations. What remains genuinely unexplained is why an act whose consequences are shared by everyone, permanently, has never produced a binding international prohibition. For the first 4 decades of spaceflight, the launch rate was measured in dozens of satellites per year. That is the environment Kessler modeled. That environment no longer exists. Since 2019, commercial megaconstellations have changed the population of low Earth orbit faster than any other development in the history of the space age. Thousands of small communication satellites, launched in batches of dozens, occupying shells at a few hundred kilometers of altitude. Here is the honest part, and it cuts against the doom framing. These satellites are, by design, some of the better-behaved objects up there. They fly low, where atmospheric drag will remove them within a few years if they fail. They carry propulsion and can maneuver autonomously to avoid conjunctions. Operators report performing tens of thousands of avoidance maneuvers per year. That is not a footnote. It genuinely matters. A maneuverable satellite at 500 kilometers is a fundamentally different risk than a dead 1-ton rocket body at 850 kilometers. But 2 things are true at once. The first is that avoidance depends on tracking, and tracking depends on the catalog, and the catalog stops at roughly 10 centimeters. Every maneuver performed is a maneuver against the population we can see. The second is failure rate. Even a small percentage of satellites that die before they can deorbit produces a steady trickle of new, uncontrolled objects. And the total number of satellites is now large enough that a small percentage is a large number. Total mass in Earth orbit is now estimated at well over 11,000 tons. That is the raw material. Every kilogram of it is a potential source of fragments. The scale comparison: you are not looking at a landfill. You are looking at a landfill where everything in it is moving at 28,000 kilometers per hour, and nothing decomposes. So how close is the tipping point? This is where the field gets carefully, deliberately uncertain, and this is the part that gets flattened in headlines. There is no single altitude at which Kessler syndrome switches on. Different models, using different assumptions about launch rates, failure rates, fragmentation behavior, and atmospheric density, produce different answers. What most of them agree on is narrower and, in some ways, more unsettling. Several long-running studies suggest that certain altitude bands, particularly between roughly 700 and 1,000 kilometers, may already be past the point where the fragment population is self-sustaining. Not catastrophically, not visibly, just slowly, on a timescale of centuries rather than years. Kessler syndrome, in other words, is probably not an event. It is a slope, and parts of the environment may already be on it. What contradicts the popular version of this story is the timescale. The cascade is not a wall of debris that appears over a weekend and locks the planet in. The realistic version is a gradual increase in collision risk that makes specific orbital shells progressively more expensive, more insurance-heavy, and eventually not worth using. The relatable version: nobody padlocks the door. The rent just goes up until nobody can afford the room. Researchers still cannot precisely model the fragmentation behavior of modern spacecraft materials. Composites and lightweight structures break up differently from the aluminum bodies the standard breakup models were calibrated on. And the sub-centimeter population, the one doing much of the actual damage, remains close to impossible to measure directly. That is the honest state of the science. The direction is clear, the rate is not, and you should be suspicious of anyone who tells you otherwise in either direction. The version that says orbit is already lost is wrong. The version that says the problem solves itself is also wrong. What the data supports is narrower and less satisfying, a measurable upward trend in fragment count, concentrated in specific altitude bands, with a timescale that nobody can pin down to better than a factor of several. So what actually happens next? Three things are already in motion. The first is regulatory. In 2022, the United States Federal Communications Commission adopted a rule requiring most satellites in low Earth orbit to deorbit within 5 years of ending their mission, replacing a long-standing 25-year guideline. European guidance has moved in the same direction. It does nothing about what is already up there. It slows what gets added. The second is active removal. ESA has been developing Clear Space 1, a mission intended to demonstrate that a spacecraft can rendezvous with a derelict object and bring it down. The mission has been reworked and delayed since it was first announced, with a target now late in this decade. Other agencies and companies are pursuing capture, drag sails, and tethers. Be clear-eyed about the scale. These are demonstration missions, one object at a time, against a population of thousands of large derelicts and 1 million fragments. This is not cleanup. It is a proof of concept that cleanup is even possible. The third is the atmosphere itself, and it is the only mechanism operating at scale. Solar activity heats and expands the upper atmosphere, increasing drag and pulling low-altitude debris down faster. The current solar cycle has been actively clearing the lowest shells, but it only reaches the low ones. Everything above 800 kilometers is untouched by it. Now the long view. The satellites in low orbit will come down. The fragments at 400 kilometers will come down. But the population above 800 kilometers, including everything created by the 2007 and 2009 events, will still be there in the year 2200. It will still be moving at 28,000 kilometers per hour. It will still be too small to see. And this is the loop that makes it matter to you, on the ground. You do not use space occasionally. You use it constantly. Position and timing signals underpin navigation, financial timestamping, and power grid synchronization. Weather forecasting depends on orbital instruments. Communications, disaster response, crop monitoring, climate measurement, all of it runs through that shell. The scenario is not humanity locked on Earth by a wall of metal. The realistic scenario is worse in a quieter way. It is a slow retreat from specific orbits, rising costs, degraded services, and a generation of missions that never launch because the risk math stopped working. The door does not slam, it narrows. 1 centimeter, 28,000 kilometers per hour, 1.2 million fragments. One paper, published in 1978, that described all of it before most of it existed. Donald Kessler did not predict a disaster. He described an arithmetic. More objects means more pairs. More pairs means more collisions. More collisions means more objects. That arithmetic has not changed since 1978. What has changed is which side of it we are standing on. There is no siren for this. Nothing falls. The sky looks exactly the same tonight as it did a century ago. The only evidence is a number in an ESA report that goes up each year, and a catalog that grows by fragments nobody launched. That is what makes it hard. Every threat we are good at responding to announces itself. This one does not. It just accumulates, silently, at 28,000 kilometers per hour, in the one place we cannot reach and cannot clean. The generation that opened this door is not the generation that will find out whether it stayed open. If this was useful, subscribe and turn on notifications. Every episode on this channel is built on real published research and real mission data, grounded in what has actually been measured rather than exaggerated headlines.